about linear algebra with infinite dimensions, you can stick around after class. Complex analysis is a good place for it to start. In fact, as a slight tangent before we start talking about vector fields, you can just imagine that if you had a power series that converged and its coefficients were square summable, that is, you could take the coefficients of the power series and square them all and add them up, and that was a convergent series, then you've got a space that's called little L2, the space of square summable sequences. So square summable sequences are like infinite dimensional vectors, and they correspond to analytic functions because you can just feed those same numbers into, in the same way that a Taylor series has coefficients that represent like sort of a vector. You can think about power, like that move in infinite dimensions still works. So there's a vector space of functions called big L2, which are the square summable or the square integrable functions, and that turns out to be things that can be approximated with Fourier series. So Fourier series are essentially infinite dimensional linear algebra. There you go. Okay, so we unfortunately for my own personal taste, are going to be talking about vector fields today. So let's talk about vector fields. So I got some feedback last time. I was already planning to do this, that there are some people in here that remember nothing about vector fields, what vector fields are, and how they work. So I'm going to go through kind of the basic sort of language, not in detail, but just to remind you sort of the languages, and we'll talk about the connection between vector fields, harmonic functions, and analytic functions, and the sort of magic of how complex analysis glues all this together. So a scalar field on a domain A, and we're going to work as a subset of R2 here, but I want you to imagine that R2 and C are going to be used sort of interchangeably depending on if we're talking about harmonic functions or analytic functions, okay? So a domain A in R2 is also a domain in C, just with the identification of xy with x plus iy. Okay? So a scalar field on a domain A in R2 is a function u of x, y, and the way that you think about a scalar field is that it assigns to each point a scalar value. It assigns to each point in A a scalar value. The usual way that you talk about this when you learn it for the first time is like the temperature map. When, when the weather comes up and shows you where the temperature what the temperature is in different portions of a map, that's a scalar function, right? Or a scalar field. The other way that you can think about it is assigning a surface to sit on top of the x's and y's, but that's less useful for what I'm trying to do here. So we're thinking a flat picture. So I want you to think of a scalar field again as you have some set A, and then associated to the set A are some collection of values attached to individual points. And obviously this is the same as having a surface sitting over the top of it, like an z is equal to a function of x and y. Okay, from a scalar field, if you make the assumption that the scalar field can be differentiated, you get a natural example of something called a vector field. So a vector field is a function, and for now we're only going to talk about one vector field in here, but I'm going to use the letter x just for a second, right? It's a function x sitting on, maybe we'll use v instead, v sitting over x and y that assigns a vector to each point in A. So same picture, you have some set A, and now you imagine to each point in the interior, a vector field is a function that says, oh, at that point, stick a vector there. At this point, put this vector here. At this point, put this vector. So it's a function that maps from R2 into R2. Right? And normally the way that we think about these things is you can think about v of x and y as being equal to v1 of x and y, v2 of x and y. So it's got two component functions, v1 and v2 is that. So because we're talking about complex analytic functions and harmonic functions running around in the background, we're going to be able to make the assumption that the things we're dealing with are differentiable. In fact, so we're working with the nicest possible version of this. The study of these things is really fiddly. You can have vector fields that have really terrible behavior. We are going to study functions that are differentiable. So the natural way of starting with a scalar field and getting a vector field is to use the gradient operator. So the gradient here. Remind you that if U is a scalar field, then the gradient of U, which is also written grad U, which is also written d by dx, d by dy, U. It's another way of thinking about what this is doing, is equal to the vector du dx, du dy. So this is a vector field because this eats x's and y's but spits out vectors. Right? So the gradient you could think of as somehow representing a derivative of a scalar field. And what this derivative measures, if you guys remember, is that the gradient of u is a vector pointing in the direction of greatest change in U. I'll clarify what I mean by that in a second. It's going to take a picture to do this. I should get my color chalk up here. So when you have this relationship, before I draw the picture of geometrically what's happening here, when you have this relationship between a scalar field and its vector field that's induced by the gradient, that's really special. It basically means that the vector field can be integrated into a scalar function. And so this function u in this case, if you have u and it's associated with a vector field grad u, this is a vector field. And this is called a potential function. Right? So if u can be differentiated, if u is continuously differentiable, to have this property, u needs to be C1. So you have to have a once continuously differentiable scalar function in order for its partial derivatives in both variables to exist. So if you have a gradient u here, and this is a C1 function, which means it's got continuous first derivatives, then this will be a continuous vector field. And what that means is that you move around, the arrows don't change very much as you slide around inside the field. Right? As you slide x and y slightly, the vector moves just a little bit. Potential functions have what are called level curves. Right? So if I took my scalar function u of x and y, and I set it equal to some constant, that's going to give me a curve, say this is the set A. There's going to be some curve inside here where this is a place where u is equal to some constant c. And these guys are called level curves. In many contexts, they're called equipotentials, is another word that you may have seen in different contexts. So if I say level curve, you also may see equipotential as a word used to describe this. But the idea is, remember, this is like the lines on which the temperature is constant on the map, right? If you look at a temperature map and there's the lines separating the different sections of the map from the 70-degree band and the 80-degree band and the 90-degree band, what's dividing those up, you can imagine here, maybe this corresponds to t is equal to 60, and then there's another band where t is equal to 70 if u was a temperature map, right? So these guys are all places where the function u is equal to different constants. be u is equal to C1, u is C2, u is C3, u is equal to C4. If u is continuously differentiable, and you write down the lines where it has the same value on all those lines, it has a magical relationship with the gradient vector, right? It turns out to be the case that the gradient vectors are orthogonal to the equipotential lines. It's one of the most important properties that the gradient has. So if you write down a tangent line to an equipotential at a point, then at that point, perpendicular to that is the gradient. So the gradient of u at a point is orthogonal to the equipotential that that point sits on, or the level curve that that line sits on. Okay, so that's your basic geometry. And so you can imagine what the gradient of u is doing is it's taking this picture and it's putting tangent vector, or like sort of these normal vectors all over this curve, right? Everywhere on this curve, every one of these equipotential lines has normal vectors sticking out of it. And the size of the vectors sort of indicates something about how steep the function is at those points. Yep?
Is it ever possible for the gradient to actually flip on the other side?
Yeah, because you can have things like where you can have like regions. So yes, because you could have it be the case that as you come up, the gradient comes to 0, which would be a point where, so if the gradient ever is 0, those are bad points in a function, right? Like if you have gradient equal to 0, that's the same thing as being locally 0 derivative, which means you lose conformality, and that means you can flip orientation. So yes.
Gotcha.
Yeah. Not for nice fields though. We're going to be dealing with nice fields that this doesn't happen to.
Gotcha.
Okay. So now does this make sense so far? Kind of what's happening here? We have a function that's put a temperature map down in a domain. We have the gradient that's telling us how, if you like to use heat as your analogy here, what the gradient is telling you is how that heat energy is flowing through the map, right? I've got usually you let negative gradient be the direction because heat flows from high temperature to low temperature. So if you were high temperature on this side and low temperature on this side, this tells you the direction the heat is flowing. So one of the hardest problems that you face when you're dealing with vector fields like this is it would be more useful if we actually knew the curves on which things flow. So the flow lines or streamlines of the function. What I mean here is if you have some graph and you draw a bunch of equipotentials inside of it, so there's a level curve of u, and there's a level curve of u, and there's a level curve of u, I can draw the gradient vector here, and I can draw the gradient vector here, and I can draw the gradient vector here. But what I'd like to do, if I'm imagining this was a fluid flowing or heat flowing, is to draw a particle at this point and then track the trajectory it took through the domain, right? Where does it go? Which is essentially describing, can you give me a curve that has these vectors, that has gradient vectors as tangent vectors everywhere along the line? I want to be able to do this. I want to be able to draw a curve, this isn't going to work for this one, where I come through and everywhere I am, this curve, everywhere it crosses through one of these equipotentials, it has the gradient vectors not as orthogonal vectors, but as tangent vectors. You can imagine if this was like fluid flowing, it'd be like dropping in some sort of like little floaty dude and then seeing where it went, right? And these guys are called flow lines or streamlines. And solving for the equation for these things, if you take Math 304, turns out to be incredibly difficult, right? These are not easy to solve for. You get a differential equation generally that's like, when you teach vector calculus, you get to the point where you write down the differential equation that describes these, and you say, well, in theory, this could be solved, do it numerically. Like that's what they say. In the book, it actually says that, right? This could be done. Here's a very simple example of finding the equation for these. Even though the geometry suggests it should be pretty straightforward, because you know that it must pass through each one of these points, and it's got to be tangent to the gradient field. So this is supposed to remind you of differential equations 1, when you guys did slope fields, and you pretended that you knew how to draw one of the curves that went through a slope field by saying, oh, well, the arrow says go this way a little bit, and then now the arrow points this way, so go this way a little bit, and then essentially you're doing something called Euler's method when you do that. which is actually the way they did it up until computers existed. Okay, so what we're going to do is we're going to put one more assumption on the scalar field U that will actually turn this into a magical solution. So one feature, okay, now I'm trying to be super concrete today. I know I'm sort of like, I haven't given you specific examples, but I'm trying to orient you towards what the big picture is here. We have some function that we've used to distribute, like, or say what the temperature is across some domain, say, and then I did the gradient, which tells you the heat flow that's happening inside of it, which is perpendicular to the lines where we have constant temperature. And I'm saying that one thing we would like to be able to do is calculate these streamlines, which are important for, say, the study of fluids or the study of heat flow. And what we want to do is we want to be able to get from U to an equation for this without having to grind through horrible numerics. And maybe to leverage the fact that we know some solutions to some special cases of these things. So we're going to get conformality into the picture at some point too. So are there questions now? I mean, I want to make sure we're all on the same page about why we're doing this. Are there questions about what we've talked about so far? Hopefully this is just a reminder and not like, oh my God, this is the first time I've ever seen this. Okay. So one sort of thing that happens when you have the setup that U is equal to, or sorry, that you've got some vector field V, which is equal to the gradient of a scalar field U, is that comes with a bunch of really nice properties. So one thing that you get is that integrals are path independent. Line integrals are path independent. So what that means is that you have some vector field and you started with a curve that went from here to here, and you calculated the integral of this path through this vector field, that it wouldn't matter how you got from here to here. The only thing that matters is the starting point and the ending point. This is like a conservation of energy type idea, right? That it didn't matter how you got from here to here, that the line integral or contour integral that you wrote down would be the same. Okay? Okay. The other thing, the other property that these things have is that the curl of such fields is 0. These are called irrotational fields. Which means they are curl of V is equal to 0. So curl, if you don't remember, I've never seen it before, is a way of locally measuring if a vector field is tending to rotate at a point. So to be irrotational means that if you drew a little tiny neighborhood and you looked at something about the tendency to twist, there's no twisting anywhere in the field. And every one of these, every integrable vector field, where you can integrate the vector field and get the potential function back out, turns out to have this property. Now you might be suspicious because I'm only working in the plane here about how curl makes any sense in the plane, because calculating curl involves the cross product, and the way you do it is you cheat and pretend 2 dimensions is 3 dimensions with 0 in the third coordinate, and then you just calculate the curl that way. It's actually worth taking the time to remind you why this is true, by the way. So what we're going to do is we're going to imagine that V, which is the gradient of U, temporarily to calculate curl, to look at the rotation of the field, we're going to think of this as being du dx, du dy, 0. So just for the moment, I'm pretending that my plane vector field is sitting in free space, and I'm going to compute its curl as a plane vector field, or as in 3D. The curl of V is equal to this guy. Maybe you've seen this formalism before, maybe you haven't. The idea is that you take d by dx, d by dy, and d by dz, and you cross it with your vector field, which is du dx, du dy, well, du dz is 0. If you do that computation, Hopefully I'm not triggering anybody here. D dx, d dy, d dz. All that we're doing is, this is a bookkeeping way of keeping track of what it is that we're trying to measure. Everything we're measuring when we measure the behavior of a vector field involves different ways of looking at the derivative. And this particular notion of the derivative measures if there's twist in the vector field or not. Ux, uy, 0. If you compute this bad boy, well, remember u and x are functions of just x and y, right? So if you take their z derivatives, you get 0. So if you finish grinding through this, I think what you end up with is something like du, you get uxy minus uyx is what ends up falling out of this thing in the k direction. But uxy minus uyx, there's a theorem that describes the relationship between those things that I told you guys the name of last quarter. And I gave you my pop quiz on, which is, what is the name that says that if a function is C2, that is twice continuously differentiable, then the mixed partials are equal to each other? Yeah?
Clairaut's.
Oh, there we go. That's right. Clairaut's theorem. You can never escape it. So this is equal to 0 whenever these functions are nice, is the idea, right? So if you have a twice continuously differentiable function, these are equal because mixed partials are equal, so the curl is equal to 0, so there's no rotation in the vector field. Okay. Of course, to say that, yep.
Do you do this cross product without pretending it's in free space, or is that just?
There's no such thing as cross product without pretending in free space. I mean, there's a notion that you can cook up to talk about rotation, but really you should think of curl as being a three-dimensional notion. Geometry gets a lot more complicated when you go above n equals 3. And n equals 2, you can always just embed. It's one of the great tricks of multivariable calculus is that you can frequently embed plane geometry into three-dimensional geometry.
So 3 is imaginary.
Yeah, I mean, like, because the cross product exists, right? So what the cross product gets you is what the axis of the rotation should be, right? And so you can imagine if you took a plane of things moving around and you calculate the curl, of course it must be the case that the axis of rotation is pointing in the k direction, right? Because if there is going to be rotation, it must be perpendicular to the xy plane that things are sitting in. So it's natural to think about this. Essentially what you're doing is, you're not really pretending that this field is, really what you're doing is you're imagining that the field sort of is, every xy plane is acting in the same way. You've got a vector field that's working like this enormous cylinder, is a way of thinking about it. And so you're just looking at the vertical axes at each point and making sure that there's no rotation around that point. But yeah, it's a computational trick. All this stuff is the thing where you see somebody do it and say, oh, I sure is lucky that worked out. Okay, so this calculation only makes sense when u is a C2 function. So C1 got us that the gradient existed. C2 is going to tell us that, that this equation holds true because the partial derivatives exist, are continuous, and we should be thinking about C2 functions. C2, remember, means twice continuously differentiable. Okay. If only there was a natural family of twice continuously differentiable functions that we've been talking about in the context of complex analysis. The real and imaginary parts of analytic functions are harmonic functions, right? And so harmonic functions are twice continuously differentiable. So what was the assumption about harmonic functions? If u was harmonic, how did we define what it meant to be harmonic? So Laplacian is equal to 0. So if I say u is harmonic, I mean u is C2 and this symbol, the Laplacian, is equal to 0. What is the Laplacian? Like, what actually is it? I mean, we wrote down at some point uxx plus uyy is equal to 0, but what is it as a vector field computation? Here's what's available to you. Divergence, curl, and gradient. Those are the operators that you can do on these fields, right? Those are the natural operations you can do. Do you actually know what this is? This is the divergence of the gradient field. So the other way of writing Laplace's equation is the divergence of the curl, or sorry, of the gradient of u. And to say that something is a harmonic function is to say that the divergence of the gradient field is equal to 0, right? So if u is harmonic, then what we're saying is that the divergence of the curl, or sorry, of grad u is equal to 0, and that means grad u is what's called a divergence-free field. Okay, that means it's a big, yep.
So is that like no sources or sinks in the field?
Essentially, yeah. Yeah, nothing's being created or destroyed, so that's a good way of thinking about it. So these actually turn out to be two very strong assumptions to make about the way a vector field works. These are about the nicest possible vector fields. So divergence, if that's not a quantity that you remember how that works, is a way of measuring if you have a vector field. If you really want the nitty-gritty on this stuff, you got to take a class in vector analysis or partial differential equations. So you have some vector field, V. The way to think about divergence is not, the way to think about rotation, curl, was you draw a little circle and see, do other vectors rotating around an axis in here, or is the rotational sort of like behavior balanced on either side, on all sides of the axis? Does all the rotational stuff cancel out? Divergence, you think, draw a box. Does the amount of vector going into the box equal the amount of vector flowing out of the box, right? So that means no box you can draw is creating energy or destroying it, is one way of thinking about it. Or creating stuff or destroying it. So to be divergence-free means that the input and the output of the vector, if you think of a fluid flowing or like energy flowing, energy in is equal to energy out. Or fluid in is equal to fluid out. Flow in, you should be careful. Okay, so to be divergence-free means flow in. I am deliberately not using the correct technical language here because I don't want to get into the weeds with it. So flux, yes, is running around in the background. I'm avoiding talking about flux. Flow in is equal to flow out is the way to think about it. That is what you mean by divergence-free. So you got this beefy set of assumptions. U is harmonic. To be harmonic means that the Laplace's equation is equal to 0. The Laplacian of u is equal to 0. It means that the gradient of u is irrotational. And it means that the gradient of u is divergence-free. Now that seems like a lot of strong assumptions to make about the way that the physical setting which is set up, right? To have like vector fields with this kind of assumptions on it. But it turns out to be the case that there's a lot of phenomena that are naturally modeled with this sort of set of assumptions. So heat flow is one, ideal fluid flow. So if you have fluid flow, like essentially water, the flow of water can be modeled with this. So you need the fluid to be incompressible and non-viscous, and water is meets. So to be an incompressible fluid means you can't smash it and like crush more into a space than can come out of it. Well, that which would violate this assumption that we have no divergence, right? Because I mean, you could squeeze things in and hold it there and not have the same amount come back out the other side. The original motivation for this was in the flow of heat. So this was originally invented to study heat flow, and then as physicists and engineers are wont to do, they said, well, once I know how to solve heat flow equations with this idea, I'm going to turn everything into a heat problem. So other things you can turn into a heat problem include things like certain types of fluid flow. Electrostatics can be thought of this way. So you get this like whole set of ideas with the strong restriction that it works in 2 dimensions. So these are 2D methods almost entirely. And there's ways of beefing them up into 3D, but you have to use either exotic math or beefy computers. And computers are beefier than exotic math is for your day-to-day engineering practice. So you just stab it into a computer and you don't care why it's true. Right? I'm not actually making fun of engineers here, but there's no, why should I have to deal with exotic transformations of harmonic functions in 6 variables when I could just throw it into a computer program and it will tell me what the fluid flow is from a certain vector field. Okay, so now I've got to tell you the magic part. This is my favorite part of the whole thing. When you have this setting, when you have the fact that you've got a harmonic function and you have vector fields that are this nice, it turns out to be the case that there is this insane relationship between the potential function, the vector field, and the streamlines for the function. So I'm going to draw a domain, A, and I want you to imagine that you have U is harmonic. Draw your level curves of the harmonic function. So these are places where U is constant. You have a gradient field sitting in the background making little normal vectors all over the place. And finally, you have the flow lines that are going through this like this. Let's see if I can draw a reasonable version here. Maybe this one curls up this way. So these guys are the flow lines. These turn out to be the level curves of the harmonic conjugate.
What?
Yeah.
That's crazy.
So you cheat. You don't solve the differential equation. I mean, you do, because the way you find a harmonic function conjugate is you integrate the derivatives with the Cauchy-Riemann equations, right? But if this is harmonic and this is where U is constant, these streamlines or flow lines are places where the harmonic conjugate of U is constant. That's the harmonic conjugate. Which means, secretly, in the background, the study of potential theory in the context of the Laplacian is complex analysis. Because what happens when you put a harmonic function together with its harmonic conjugate? You get an analytic function, right? And in fact, every analytic function will give you a harmonic function and its conjugate pair, which means you have an absurd quantity of harmonic functions to work with. Every analytic function gives you a harmonic function and its conjugate. So I told you that the streamline problem is hard to solve in general, and it is, but in the context of harmonic functions, you can find the streamlines by just taking the harmonic conjugate and setting it equal to constants. Yep.
Is this kind of when we break the analytic function into U and V?
Yes, that's what I'm going to do exactly. It's actually a consequence of the Cauchy-Riemann equations, right? The Cauchy-Riemann equations describe the relationship between the U and V by saying Ux is equal to Vy and minus Ux is equal to, minus Uy is equal to Vx. That says that the vector field generated by U and the gradient field generated by V are like rotated 90 degrees to each other. So if U is equal to C are equipotentials and U star is the harmonic conjugate of U, then U star is equal to C are the streamlines. Yep.
Would this rationale make the map from U to U star conformal?
You should think what we're going to do here is we're actually going, we're going to use conformality here, but we're going to use conformality to preserve this geometry.
Right.
So what we're going to assert is if we took this picture and we fed it into a conformal map, even though we would be distorting all of the lines by changing the domain to something else, we would still have the same relationship between the equipotentials and the streamlines.
Okay.
And that means that we're going to be able to use conformal maps to make these domains nicer but still preserve that harmonic relation, the harmonic-harmonic conjugate relationship. So we're going to, with this setup, this basically opens the door for us to use conformal maps to study equations. So that means that we define a function f of z is equal to u plus I times u star. Here, f of z is f of x plus iy. We reimagine this in the complex setting. One, that function is analytic because its real part is harmonic and its imaginary part is also harmonic. That's what the harmonic conjugate does, right? Is it gives you an analytic function. So f is analytic. That's nice. And it's usually called the complex potential. A complex potential. And the idea is that if I give you an analytic function, so given f of z is equal to u plus iv analytic, the real part of f, which is equal to u, is harmonic. And so we'll create an irrotational divergence-free vector field that describes flow lines on equipotentials. And the imaginary part of f, which is equal to v, is the harmonic conjugate. And the way that a scientist or an applied mathematician or an engineer would look like this would be to say, well, that means I can pick and choose my favorite analytic function. I can look at a physical scenario, and I can just wiggle these things around until I get the behavior that I want. So I can pick a function. And I can say, well, what does it do? What does my function do? And then choose an analytic function that gives you the correct sort of physical behavior, and then use that to model scenarios. So the idea is every analytic function gives you a picture like this on its domain. And every picture like this pulls back to an analytic function that you can use complex analysis on. And so even though maybe the set of problems that you can work on is sort of constrained, it turns out to be huge numbers of situations can be thought of in this way. You can beef it up even slightly if you allow yourself weird complex integration. But is this okay so far? This is sort of how it all comes together. The sort of partial differential equation, Laplacian. You actually might wonder, a good question for you to ask me right now would be, where the hell did the Laplacian come from? Like, why would anybody have thought that that was something that you would want to study? Right? I mean, if that has not occurred to you, it should occur to you, because did I just pull that out of the air? Like, oh, look, if I let the Laplacian of u be equal to 0, we'll just call that a harmonic function and look at all the properties it has. Why would that have been studied in the first place? So they didn't start with Maxwell's equations. They were working with something Fourier cooked up.
Isn't it like a tendency for a function about a point to be average that?
Yes. So what's the equation that tells you that? You can throw weird words at me like isotropy if you want, but I don't want to hear about isotropy right now. I want to know where the Laplace equation comes from. All of this beautiful structure that connects harmonic functions and equipotentials and flow lines and complex functions, all of this stuff came from something that was motivated by something. So okay, I know some of you are here are engineers, and I know a lot of you in here are in applied math. Can you tell me an equation where this comes up? Remember that we wrote down that this was equal to uxx plus uyy. Is there an equation that you know, that you've seen, that has that term in it? The heat equation. That's a good one. It's one of the fundamental, it was the first partial differential equation, was the heat equation. Right? It was the very first one that was studied, was the heat equation. Could you tell me what the heat equation says, ignoring all constants because we're mathematicians and don't care about materials? Just the basic, yeah, the heat equation on a rod. So I'll give you the left-hand side. I will give you the left-hand side of it. du dt. So this is the heat equation. And what the heat equation describes is the way that heat tends to flow in material, right? It says that the way that you flow physically and sort of like is going to depend on the average temperature around you. So if you say that there's no time dependence in the equation, you take that away, you set that equal to 0, you get Laplace's equation. So Laplace's equation is the simplest possible form of the heat equation. Laplace's equation says, throw time dependence in T away. If you take this and you set that equal to 0, you get this. If you like, this is like a homogeneous equation, solution to this equation. So the non-time dependent part of the solution to this equation is this one. And the reason, we're not really going to do much with this, I hate it when people say things without actually saying why we're doing it. This is where this originally came from. Was Fourier wrote this equation down because he was interested in the way heat was being conducted in metals. He wrote down this equation thinking that it has to do with, well, you look at the average of the way the temperature is distributed around every point, and then you connect that up with the flow over time. Yep.
I know in the one-dimensional case that the Laplacian is just UXX, right? And it relates the concavity of the concentration to the rate of change.
Yep.
So when you beef up to 2 dimensions and beyond, how does this relate to concavity in the same sense?
So if you think about okay, now we're going to go deep cut here. You guys remember 241?
Sure.
Okay, 241 you did that's multivariable calculus. So calculus 4, where you studied mostly 2 variables, right? And one of the things you would have studied in 2 variables is the second derivative test for functions of 2 variables.
Sure.
And one of the things you classified when you did that was you were looking at concavity not just in one direction, but concavity in multiple directions. Right? And you built this matrix derivative of this that basically told you in the x direction you're concave up, in the y direction you're concave down. So you have this sort of, it's possible that you could have mixtures of concavities that are not all up or all down. Right? So this does measure concavity, but in the sense of locally all increasing, locally all decreasing, or one direction is increasing and the other is decreasing. That's basically the behavior you can have locally in the surfaces like this, throwing away the case where the derivative disappears because those suck.
Okay, so this could be satisfied theoretically when the concavity is not, when you're at like a saddle point.
Yeah.
Okay.
Yeah, so the flows can be, you can have, if you think about distributing not just the surface, but the temperatures that you put down in a map, it's possible that you could be increasing in one direction and decreasing in another, right? If I'm 60 degrees right here, or I'm standing on a mountain and I'm 600 meters up, I could definitely go down in one direction and up in the other. If you've ever walked up like a ridge or something on a mountain, right? That's like, that would have a description here where you're going to have multiple concavities mixing with each other. Okay, so I'm going to leave today with the easiest possible example of one of these things. And then next time we're going to do a basic example of how conformality gets into the picture to solve an actual physical problem. So here is what the babiest possible version of fluid flow looks like. I'm going to give you a complex potential. How do I know it's a complex potential? Because all I got to do is write down an analytic function. Here's an analytic function. F of z is equal to z. Look at that bad boy. Maybe we'll put an alpha in here. Maybe we'll put some velocity on it. That's like AZ, alpha z. Okay, what is the real part of F? Alpha x. And the imaginary part? Alpha y, because this function is alpha x plus I alpha y.
Alpha real.
Alpha is some real constant. Yep. Alpha is real. What's the gradient? Okay, so this function is u. U of x and y is equal to alpha x. And v of x and y is equal to alpha y. What's the gradient of u? alpha 0. To each point xy, the gradient assigns it the vector alpha 0. Every point is assigned the same vector. It points to the right with magnitude alpha.
Why is it not alpha?
Well, what's the derivative of alpha x with respect to y?
Oh, of u. Gotcha.
Yeah, not z, u, right? We have to come from the complex setting to two real variable setting. So if we draw a picture of what this looks like, let's just pick a nice domain to work with. I don't know, like the upper half plane. That seems like a reasonable domain because I can conformally map it around to various things. You guys could use right half planes if you want. This isn't control theory, so. The idea here is that like you get vectors attached to every point, and each one of those vectors is the vector alpha 0. So this represents, okay. Now imagine that I've got this boundary out here that's not part. I have to make a domain, so it's an open set, right? Is it reasonable for this to model the flow of a fluid? That's the first thing that you should be thinking here, because this is the way that the people that did this originally. As a basic model for the way the fluid flows, you can imagine I've got some infinite plane. Is this a reasonable model for the way that you would expect? Remember, we don't care about the velocities necessarily. We're after the streamlines, right? If you picked the points where this function was equal to some constant, you would end up with lines that look like, I say, alpha x is equal to c means x is equal to c over alpha. So the equipotential lines here look like this. They're vertical lines, right? The places where we have level curves here are vertical lines. The flow lines for this, which are the places where the harmonic conjugate is constant, alpha y is equal to some constant when y is equal to c over alpha. Well, those are horizontal lines. And so for a very, very basic version of a solved problem, with the sort of naive approach to fluid flow would be to say, this would model the flow of an ideal fluid in the upper half plane. You just have an infinite amount of fluid. Who cares about what's happening in infinity? It's flowing with constant velocity. The streamlines look correct. The velocity vectors look correct. Everything is, with a fluid, is any of the fluid leaking out? No, which means that du dn is equal to 0 everywhere. It's an insulated boundary. Fluid flows parallel to the boundaries of, you can just imagine there's no turbulence or anything here. It's just like fluid flowing in a plane, right? Lazy, wide river flowing on this infinite plane. That thing right there is what's called a standard solution for naive fluid flow, right? It's not very interesting. That's just not an interesting case. Yep?
Do we kind of just try not to think about the Riemann sphere and like weird mappings where we...
So we're not going to, so the Riemann sphere would be interesting. So what would actually happen on the Riemann sphere here? All of these things are somehow being absorbed at the point of infinity, but we're just going to, so in this case, this function is unbounded at infinity, which is bad in a lot of physical settings. For us, we're just going to ignore it and say, you know what? As long as I only work on the plane, everything's going to be cool. I'm like sure I map unbounded domains to unbounded domains and not worry about infinity. Okay, so what we're going to do is we're going to take this really easy model and we're going to conformally map it to significantly more complicated domains. And what it will do is it will track what happens to the streamlines if the boundary represents a shape that we're interested in studying. So for example, if I took this picture and I turned it into, conformally, I turned it into a picture like this, where I take the upper half plane and I map it to this set. If I do that conformally, it will pull the streamlines and equipotentials with it and distort them. And what we'll see when we start doing this is the images of the flow lines start doing this. So it's a way of analyzing what happens by starting with the basic picture and conformally distorting it. We can pick up behavior around significantly more complicated objects. In the very first example, you might want to work this out. What does the map z goes to z plus 1 over z do? That's the very first conformal map we're going to look at next time. So we've got the setup. Next time, we're going to actually look at concrete examples. These actually can be visualized in Desmos. Yep.
Are we going to do that on like
We are, so yeah, so